Hello guys, welcome back to Maison African Motives, working on industrial electronics N3. In this platform, we shall be having a revision from the question paper, which was written in February 2022. So we are going to have a full paper worked out for this part. So be careful when answering question papers, especially on your finals, to read the instruction. Every part of the instruction that you're given is for you, all right, to use or to apply in your calculations, especially this part of rounding off your answers to 3 decimal places, depending with what you're given. And also, all calculations must have, take note, they must have the following 3 steps: the formula that you are using, the replacement of values, the answer, and correct SI unit. So this is the most important part in your calculations that you're supposed to show these steps. So we're going to quickly rush through the questions. We are given the first part of the question, which is question number 1, which is on section A. Okay, the first part we are given to indicate whether the following statements are true or false by writing only true or false next to the question number. All right. A covalent bond is formed when atoms lose valence shell electrons. This is actually false. All right. So this is false. When atoms lose valence electrons, that is we are talking about the valence electrons. Remember, these are the atoms in the outermost shell. All right. So of which a bond, it's a covalent bond. It's a combination of two different atoms that you're going to have from different bonds. Then when you combine them electronically, depending with the type of bond that you are using, all right, which is different from the loss of valence electrons, all right? 1.12, a given feedback is used in an open loop operation amplifier circuit. An open loop does not have a feedback. It's a straightforward. It does not have a feedback. This one, this is false. A decrease on 1.13, a decrease in the base current of a common emitter amplifier causes an increase in voltage measured between the emitter and the collector. All right, this is true. A decrease in base current, this is actually true. A thermistor is a semiconductor device that acts like a piezoresistive resistor. No, this is wrong. A thermistor. This is false. All right. So this is actually false. Doping refers to the addition of impurities into an intrinsic semiconductor to improve its conductivity. To improve its conductivity properties. That is the conduct. In this case, that is true. This is addition of impurities into an intrinsic semiconductor to improve its conductive properties, which is actually true. All right, so this is what we have on 1.2. Choose a term from column B. So in this case, we are given that matches a description in column A, right? Only the letter A to J next to the, okay, to the question number. So we are given column A 1.21, movement of charges of the same type or from a high concentration of free charge carriers to a low concentration of free charge carriers. Okay, so this is diffusion. Do you have diffusion in this case? All right, so you've got the diffusion current. All right, so this is going to be diffusion current, which is D. So you've got a D here. 1.22, time it takes a diode to recover from forward conduction and begin to block reverse current, or at the time that is taken by a diode to recover from forward conduction. All right, this is the recovery time. All right, so this is the reverse recovery time, which is E. So this is the recovery time, which is the reverse recovery time. The base emitter and base collector junctions reverse biased. If you reverse bias a base emitter and a base collector junctions, what is going to, this is a cut-off region, this one, all right? So this corresponds with a cut-off region, which is F. You are given a unipolar voltage operated device where current flow is controlled by an electric field produced by a voltage between the gate and conducting channel. All right, which is this is a FET, J FET. Okay, do we have which is A? All right, so this is a J FET, which is on A. All right, so this is A. So actually, this part you need to work with more of your theory. Yeah, theory part. It can actually help a lot. Okay, method used in an SCR in which a current is pushed in the opposite direction and the normal forward conducting current to switch it off. All right, to switch it off. This is the forced decommutation, all right, which is on C. Forced decommutation, which is on C. All right, so that's a forced decommutation, this one, which is C. All right, so these are the typical answers that we had. So as you can see, it's best that we work with our theory much. Then here we are given 1.3. From the list that we have, these are the answers that you're given. You're going to choose from these words to match whatever part that you're given as a sentence on the other part. So you're given on 1.31, a galvanometer is a series with a high resistance is called a, what is the name that is given to a galvanometer that is having high resistance? So that's a voltmeter, all right? A voltmeter, all right? Which is a voltmeter in this case. So this is a voltmeter. Or let me just write the answer here. This is what matches 1.31, a voltmeter. Random errors are caused by factors after all systematic errors have been accounted of. All right, so this is unknown factors. All right, when it is caused by unknown factors, unknown. So this is just inserting. We do have unknown here. We've got unknown factors. All right, so that is unknown factors. So this is the one that we are going to use on this part of 1.32. Saturation occurs in a transistor circuit when both the base emitter and the base collector junctions are forward biased. So this is forward when both are forward biased, when they are forward biased, which is this one, which is 1.33. Okay, then this part we are given that it occurs when the reverse biased applied voltage is large enough to dislodge electrons from their covalent bonds and increase the charged carriers into a conduction band. This allows for the flow of large currents without significant damage to the junction, damage to the junction. That's a Zener breakdown, this one, the Zener breakdown, all right? This is a Zener breakdown, which is 1.34. So this is a 1.34. You're going to write Zener breakdown in this case, all right? When parallel resonance occurs, the circuit, the current in the circuit will be, all right? So remember, the current is going to be minimum. Why? Because remember, in a parallel resonance, we are talking about the impedance. We are going to have our impedance, our current will be equivalent over V over ZD. So this ZD is different from the Z that we have in series. Remember, in series, we have a condition where Z is equal to R, but this part is different. This one is going to give you a maximum resistance or impedance. When this is maximum, it means the current is going to be, remember, it's an inverse with current. So current will be minimum in this case. All right. So this is what we have in this case. All right. We've got our minimum. Then various options are given in 1.4 answers as possible answers. So these are possible answers that we are given from these options. So let's see what we have in this case. So the first part we are given here, we have got let's see. Okay, let me just try to do this. We are given on 1.41, a cathode ray or oscilloscope displays a graph of waveforms based on, if we are dealing with a cathode ray that is, it's going to work with the voltages, all right? So this one, it uses voltages, which is B. So the best answer here is a voltage. An amplifier can be classified as class A amplifier when the bias point is all right, is selected so that there is a current flow during the entire input signal, this part here, which is a B. All right, so the B is the best answer that we had in this case. All right, let's check the other part. We are given that in this case, from this part that we have, which one of the following sentences statements correctly describes the characteristics of a good operational amplifier? All right, a very high voltage gain, a very high input resistance, and a very low output resistance. All right, which is true, which is correct. A very high voltage gain, very low input resistance, which is wrong. So this part is wrong. And a very high output, which is wrong. A very high voltage gain, very high input resistance, and the output is supposed to be low. All right, so this one, a very low voltage gain, which is wrong. So the first part here is the best answer. That is the one that you're going to have. From the figure that we have, it shows a phasor representation of a voltage V across a combination of a resistor and an inductor. That is the V, which is the resultant voltage in this case from VL and VR. What is the magnitude of voltage V? So the magnitude is the resultant of the two, where we know that V is equal to the square root of VR squared plus VL squared. So our V is going to be the square root of VR, which is 150 squared plus 110 squared. So this is going to give us a value of 186. So we're going to have 186, 0107 and so on. So which is to 3 decimal place, it is going to be 0, 011, which is 186, 011. 186,011, which is on C. So the best answer there is supposed to be a C. All right. Determine the current I3 in Fig 3. All right. So from our Kirchhoff's law, we know that the sum of current flowing into the circuit is onto a junction. This is our junction here. So this current flowing in is equal to the sum of current flowing out. So you can have this as current flowing in is equal to the sum of current flowing out. That is I1 and I3, I4, they are facing into this point at this point. So these two, they are facing the junction, I1 and I2. So if we add 7 plus 3 from I1 and I4, this is supposed to give us I2 and I3. These two, they are flowing away from the what? From the junction. So these two added together, they must give us these two. So it's going to be 2 plus I3. So that is it. 7 plus 3, which is 10, is equal to 2 plus I3. So we can determine I3 by transposing. This is going to be 10. That's 10 minus 2, which is equal to I3. So that means I3 in this case is going to give us 8. All right, so that's 8 amps, which is a positive, and the positive answer for 8 amps is corresponding with D. All right, so these are the typical questions, as you can see. On section A, total having 20 marks, depending with the paper that you are having. Is it having section A, or they are just having questions direct? All right, on question 2, we are given question 2 in section B, which is an application of our DC theory in this case. Calculate the following with the aid of Kirchhoff's laws. So you're given to use Kirchhoff's laws in this case to calculate or to determine whatever that you're given, or to attempt this typical question that we have in this case. All right. So the first part of the question, we are given to calculate the following with aid of Kirchhoff's law. 2.1. The equation for loop 1, which is A, B, C, D, E, F. All right, so we've got A, B, C, D, E, F, which means we are referring to this whole part of the circuit, this whole part right around the circuit, this complete loop. This is what we are referring to as our loop 1. All right, so from loop 1, what are we actually having in this case? All right, so from our loop 1 in this case, which is A, B, C, D, E, F, back to A. So this we can even have it back to point A. We can see that in terms of, remember from our Kirchhoff's law, the voltage that we have, the total voltage, which is the voltage of the circuit in this case, is equivalent to the product of what? Of current and resistance right through. So we are going to be multiplying current to the resistance, current to the resistance, depending with the current that is flowing across that circuit or across that path. All right, starting from current I1, this current is going up, this arrow is going up, which means we are maintaining the positive. So this current I1 in this branch, it is going to affect R3. In this branch, I1 is going to affect R3. The same current I1 is going to affect also R5. These two, they are in the same branch. So meaning to say, we shall have the product of current and resistance, which is the sum of R3 and R5. So this is going to be R3 plus R5. We move on to this branch where we've got I2, because this is going to flow into this branch with I2. Still, we are maintaining the direction. Look at I2. It is still maintaining the same direction with our arrow, with the direction of current flow from the voltage. This is positive, negative. So positive, we are going this direction. So it's maintaining that direction, which means I2 is going to be positive, affecting R2 and R1. These two, they are in the same branch. So we're going to have plus I2 into R2 plus R1. So you shall add these two together. So this is what we have in this loop, whereby our VT is the total voltage of 12 is equal to I1 into R3 plus R5. So if we add R3, that's 20. R5, that's 33. So this is going to be 20 plus 33 times I1 plus R2 plus R1, R2 plus R1, that's 10 plus 15. So this is going to be 10 plus 15 times I2. So we have formulated an equation in this case. All right, so 20 plus 33, we can add these together. This is going to give us 53. So that's 53 I1 plus 10 plus 15, which is 25. So this is going to give us 25 I2. So we can have this as an equation from our loop 1 in this case, which is the loop which was taken from A, B, C, D, E, F, A, back to the point A. All right. So that is how you just attempt these typical questions, guys. You have to work with the circuit that you're given, working with the direction of current properly. All right, we move on to the other part of the question, which is on 2.2, the equation for loop 2, which is A, B, E, F, A, B, E, F, which is this part here, that is A, B, E, F. All right, so I'm just going to remove this part that we had so that it is not going to affect us in this case. All right, so this is our part. I'm just going to remove this part here. So this time we are working with the A to B to E to F like this. This is the path that you are going to follow in this case. So this is your loop 2. So from this loop, still applying the same concept or the same idea that we had before, we are going to see that, okay, this is the loop that we are working with in this case. All right. So from loop 2, which is AB, we are given this as AB, E, F. All right, so this is what we have back to the point A again. So according to the direction of current, we still have the same scenario, the direction of current, which is the same, but we have to take note this time, we are going to be from A to B, then to this branch of B to E. So you follow the branch, guys. This is what you do. The voltage, we are having a voltage source in this loop that we are having. There is a voltage source. So meaning to say you shall have your total voltage equal to, let's start with the first part. We are moving from A to B. But this part of AB, it is also part of E to F. It's in the same branch. This part with EF, it is the same root to this one. From EF, A, this one, it's the same root. So meaning to say these two resistors, they are going to be affected in the same path that you are taking, which is the R5 and the R3. They are going to be affected by the same current, which is I1. So you're going to have the same part I1, which is R3 plus R5. We move on to the branch from B to E. From this part that we see here on this part from B to E, there is a current which is affecting, which is I1. We are already given as I1 minus I2. So this was supposed to be our I3, but you are given this as I1 minus I2. And what is important is it is still flowing this direction going down. So we're going to affect this as I1 minus I2 multiplied to this resistor R4. There is only one resistor. So this is going to be plus because we are maintaining the direction of this arrow of the loop, the direction of flow of current. So it's going to be a plus. So that's plus I1 minus I2 into R4. So whatever that you're going to get, we are going to multiply by resistor R4. All right, so this is what we had from this. You work with the circuit that you're given. All right, so you can insert the values from what we are given. In this case, we have got the values. VT, which is the total voltage of 12, is equal to I1, which we do not have. So we've got R3 and R5. We added this R3 plus R5. We added this before. We got 53. So this is going to be 53 times I1. All right. So we are going to have 53 I1. Then we move on. In this case, R4. We have R4, which is 30 ohms. So this is going to be plus 30 into I1 minus I2 in this case. So we have to expand this bracket so that we can formulate an equation for this loop. All right, so expanding this, we are going to have 53 I1 plus 30 times I1, which is 30 I1. 30 times minus, it's a plus, and the minus, this is going to give us a negative 30 I2. So you can collect like terms, that is current 1 to current 1. So 53 plus 30, this is going to give us 83. So you're going to have 83 I1 minus 30 I2 like this. All right. So this is the second equation that we have formulated from the loop 2 that we were given as A, B, E, F, A. All right. So from this part that we are given, sorry for that. From this part that we are given, we are now asked to solve or to calculate the values of current, I1 and I2, all right, which is 6 marks for that. All right, so how are you going to attempt this typical question? From the currents that you have, or from these equations that you formulated, we've got our first equation from loop 1, which is this part that we formulated. So I'm just going to write these equations aside so that we can formulate them and we can work out them. So this part, I'm going to start with the variables. So this is question 2.3. All right, so this was 2.2 here. Let's take note. This was 2.2. This was 2.1. So this was your 2.1. All right, so on 2.3, that is where we are asked now to solve this equation. So from equation 1, I'm going to take this one from loop 1. I'm going to start with the variables. So this is 53 I1 plus 25 I2 plus 25 I2, which is equal to 12. All right, that's my first equation. Then from this second loop, I got 83 I1 minus 30 I2. So that's 83 I1. We've got 83 I1 minus 30 I2. So this is 30 I2, which is equivalent to, that is 12 in this case. So this is equal to 12. We are going to equate this whole part to 12. All right. So this is what we have, guys. We have got our equations that we have formulated, simultaneous equations. You are now back to mathematics. This is no longer about industrial electronics or whatever that you're doing. This is about maths. You are solving simultaneous equations. Which is the best method that you have? Are you going to use substitution method? Are you going to use elimination method? Depending with the method that you're given. All right. So the best method that we can just apply in this case is our elimination method. So in order for us to calculate, let's say I want to calculate current I1. I want to start with current I1. That means I'm going to eliminate current 2. All right. So to eliminate current 2, that means we have to multiply. We interchange these numbers that we are given in this case. If you are to take note, we interchange I2, that is 25 and 30. All right. So we are going to multiply by 30 on top, 25 below. So that is what you do. If you want to calculate, let's say you want to start by calculating I2. If you are to calculate I2, at that moment, you are going to eliminate I1. So you eliminate I1. To eliminate I1, you just multiply by you just oppose these terms. This is 53, this is 83. So you have to make sure that you have got the same term. So you oppose these terms. 83 on top, 50 like this. You multiply by 83 on top, you multiply by 53 down these two. So if these two numbers can be reduced, you can reduce these numbers. Let's say you're multiplying on top by 20, down you're multiplying by 4. You can reduce 4 into 4, that's 1. 4 into 20, that's 5, which means you multiply by 5 and what? 5 and 1. But in this case, we can't reduce these terms that you are given, which is 83 and 53. So we are going to multiply with this. So that means if I am multiplying this part, I am eliminating I1. So if I am eliminating I1, I am calculating I2. So that is what you're supposed to be very, very careful. What you eliminate, you are calculating the other current. All right. So let's multiply. And when you multiply, you are multiplying every term of this equation by 83, every term of this equation by 53. All right, so that is the idea of the question in this case. So it's 83 times 53, which is going to give us 4,399. So this is big, 4,399 I1. 83 times 25, which is 2,075. So we are going to obtain 2,075 I2, which is equal to 83 times 12, which is 996. So this is going to be 996. Okay. Like we said, down we are going to multiply by 53, everything by 53. So it's 53 times 83, which is going to give us 4,399 I1. Then 53 times minus 30, that is going to be minus 1,590 I2. 53 times 12, this is going to give us 636. So from there, we can see that on I1, these two terms are the same. It's positive is positive. So when the signs are the same, when the signs are the same, subtract, we are going to subtract to eliminate the term. Subtract to eliminate the given term. All right, so that is what you're going to do in this case. Given a consideration where the given signs are the same, there's a minus on top, there's a minus below, you subtract, you eliminate that term. There's a positive on top, there's a positive below, you subtract the terms, you eliminate those terms. So that is how you can actually have this. So in this case, these two signs are the same, so I'm going to subtract. If the signs are different, you add. If the signs are different, you add. But if the signs are the same, you subtract. So that's, if we subtract these two terms, you're going to obtain a 0 in this case. So you do the same thing throughout. 2,075 I2 minus. So take note, this is a minus affecting a minus. So it is going to be a plus. So this is going to be 2,075 I2 plus 1,590 I2 like this. So if we add these two terms, we are going to obtain 3,665 I2, which is equal to, we do the same thing, we subtract 996 minus 636. This is going to give us 360. So the sign that you use here, you use it throughout. You apply with that sign throughout. Since we want to calculate I2, we can divide by 3,665 both sides, so that we can take rid of this term affecting I2, so that we are going to obtain I2 in this case. So 360 divided by 3,665, if you are to simplify properly, this is going to give you 0,098 in amps, of which you can change to milliamps. If you want, you can change to milliamps. or you can just leave your answer like that. To 3 decimal places, remember the instruction. So after obtaining the current I2, you can do the same thing to calculate I1, or you can just substitute. Since we have the value for I2 in this case, we can simply substitute. So we are going to substitute I2 into any equation. So you substitute into any equation, into any given equation that you're having. So in this case, I'm going to substitute for into equation 1. From equation 1, we were given 53 I1 plus 25 I2, which is equal to, I'm going to take with that one. From equation 1, this is the one that I'm going to use. We're given 53 I1 plus 25 I2, which is equal to 12. So from this part, I have the value for I2 that I calculated. So I'm going to substitute now the value for I2 here. So this is going to be 53 I1 plus 25, that is 25 into I2, which is 0, that's 0, 0.098, which is equal to 12. So I can calculate the value for I2, or I can make I2 the subject of the formula. I1 the subject of the formula, or I can just simplify direct. Okay, so if we are to multiply in this case, we can just combine everything in this case, or you can transpose the easiest. Let's just transpose this term to this side of the equation. So if we are to transpose, this is going to be a negative, all right? So, okay, so this one wants to save for some time. So this is going to be 12 minus this product of 25 times 0, 0.098. So since we want to calculate I1, we can divide by 53. We can divide by 53 both sides. That is I1 is equal to, so maybe you calculated this value, it's still fine. You can calculate this value for the product of these two, or you can just combine everything at once. So if you have to combine everything at once, this is going to give us something like 9.55, sorry, over 53, which is going to be 0, that's 0, 0.180 if you round off to 3 decimal places from your calculator. So make sure that you use your calculator also properly on your simplification or on your calculations. All right, so this was the question that we had on DC theory, working with Kirchhoff's law, application of Kirchhoff's law that we had. So we have to be very, very careful. The formation of equations from this part, how do you form the equations? From the diagram that you're given, the loop that you're given, you work with the loop that you're given. Sometimes you're not given the loop, then you choose the loop for yourself. You choose the one that is best for you. Okay, so that was our question 2. Let's check the other part on question 3, which is on AC theory, where we are given a parallel circuit with a resistance and inductance on top, and also a capacitance, which is an RLC circuit, parallel circuit. All right. And also we are given FR, which is the most important part for you to take note. This FR means that this circuit that we see is at resonance. That is the resonant frequency that we have. So we need to say whatever that you are dealing with under this question, it's under resonance, parallel resonance in this case. All right. So the first part of the question was to calculate the resonant frequency. They even told us in this case to calculate the resonant frequency of the circuit, which is 2 marks for that. Okay, so for resonant frequency, what is important is for us to understand the formula for resonant frequency in this case. Like I said, this is at resonance. So what we have in this case, so this is 3.1, all right? So remember that the resonant frequency is equivalent to 1 over 2 pi, the square root of LC, which is our resonant frequency is going to be 1 over 2 pi times the square root of LC. Our L in this case is that our inductance, which is 25 milli, which means times 10 to the exponent of -3. That's times 10 to the exponent of -3 times the capacitance, our capacitance, that's 125 micro, that's times 10 to the exponent or to the power of -6. So this is going to give us the resonant frequency. Remember, frequency measured in hertz. So taking your pi to be 3.142 is given, or you can just use that pi of your calculator as it is. So from that one, we are going to obtain 228,4 705. So the 5 is going to change this into 1. So which is hertz. Okay. So remember, resonant frequency is measured in what? In hertz. All right. Just like frequency, a normal frequency in this case, the current flowing through the coil. Take note, we are talking about the coil, which is the inductor. That's your coil, the inductor. So the current that can flow through the inductor is supposed to be equivalent to, let me just have this formula here. So the current that is going to flow through the inductor is going to be the voltage that is in parallel. Remember, voltage is the same over the resistance across that inductor, which is the inductive reactance, which is XL. If you are to check here, we have got the supply, which is the total voltage of the circuit. It's a parallel, so which means this voltage that we see is the same. We've got 240 volts here. We also have 240 volts here. So in this case, the inductor, we have to calculate its reactance, which is the XL, the inductive reactance, from these 25 millihenries that we are given. All right, so that we can calculate the current flowing. All right, remember that XL, which is the inductive reactance, the one that we do not have here, can be calculated from XL is equal to 2 pi FL, where XL is equivalent to 2 pi times the frequency, which is the resonant. We are at resonance in this case. So that's 28,471 times our inductance, which is L. Remember, L is 250 from that diagram. Is 250 times 10 to the exponent of -3. So this is going to give us XL, which is 24, which is going to be 44, not 24, 44, 722 to 3 decimal places, okay, which is measured in ohms. So the XL was actually limiting us to calculate the current across the inductor. So we can now calculate this from the total voltage of the circuit that we are given of 240 volts. That means we can substitute into our formula for the current across the coil, which is the current across the inductor, the voltage of 240 volts divided by the inductive reactance of 44,722. If you use your calculator properly, this is going to give us 5,36648. 5,36648. So this is going to be 366, okay, in amps. So this is current that is measured in what? In amps. All right, so that is what we have in this case. Remembering that this is a resonance, parallel resonance, where we also know that this XL that we are referring to is the same as the XC. So XL and XC, they are actually the same. So this XL and the XC, they are equal. Also, the IC and the IL, they'll be equal, which is very, very important in resonance. That means we can take this as an advantage also in consideration of other part of the questions that will be given. All right, so we are given on 3.3 now to calculate the current through the capacitor. All right, so if we are to take advantage the capacitor, this is what we have, which we said in a parallel resonance or in resonance, we are going to have these two being equal. These two being equal, the current of the capacitor and the one for the inductor, they are equal. So we can take this as an advantage to say, since these two are equal, it means since current IL is equal to current IC, that means IC is equal to IL, which is 5,366 amps. All right, so that is what we have in this case. These two, they are equal. All right, so that is what we have. Or we can calculate XC, since we have got the capacitor here. We can also calculate, we see that these two, they are equal. So you can calculate XC. Then from XC is equal to 1 over 2 pi FC. Then IC is going to be VT over XC. Remember, I said in parallel voltage is the same. So you can even apply that concept. Still, you're going to have the same answer. Calculate the total current that flow through the circuit. In this case, 3 marks for that. All right, that's 3.4, the total current. So remember that the total current can be taken from all right, let me write this one. Remember, we are at resonance. The total current is taken from the voltage over the dynamic impedance or the dynamic resistance, which is the impedance in this case. If you still remember from the first part that when when we were doing that theory, there was a question which was talking about the current that you're going to have. Is it minimum or maximum current and so forth? And I explained about this ZD. But we have to calculate because we do not have that. So that means we must calculate our ZD, where ZD, that is our dynamic impedance, is given as L over RC. That is for impedance or for resonance in this case. All right. So this we can take from the values that we have. We've got our L, 250 millihenries, R, which is 27, C, which is 125, so that we can calculate our ZD first, or in this case, all right, so that we can calculate the current later on. So that means our ZD is equal to inductance L, which is 250 millihenries. So that's 250 times 10, 250 times 10 to the exponent of -3 in this case, divided by the resistance, which is 27 times 125 microfarads. All right, so this is going to be 27. So it's everything over 27 times 125 microfarads. So simplifying from your calculator, your dynamic impedance is going to be 07407. So this is going to remain as a 4 in ohms. All right. So this can help us now to calculate the total current from the total voltage, which is from our circuit, that's 240. So we are going to have 240 as our total voltage in this case. So it's 240 over our ZD, which is 24,074. All right, so if you simplify properly from your calculator, this is going to give us 3.2, 40000 and so on, which is 3.24 amps. All right, so that is what you're going to have as the total current. Then the last part of the question on 3.5, on question 3, which is 3.5, is to draw the phasor diagram for the circuit. Remember that we said IC and IL, they are equal in a parallel circuit here. IL and IC, they are equal. So meaning to say we are going to have a straight, it's going to be a straight vertical that you're going to have in this case. So you're going to have a straight vertical line. You must draw a straight vertical line representing IC. Remember, current IC is on top from our civil concept. This one from our civil, like this. All right. So in terms of capacitance, we know that current is going to be on top. In terms of inductance, voltage is going to be on top. So in this case, if we are dealing with a two, when they are combined, these two, they are equal. So we can have our IC on top, which is our for the capacitance, all right? Then our IL down, but these two, they are equal at 5,366 amps. Remember that current that we had, which is 5,366 amps. All right, but we also have the total current. Also, this one, we are not going to have it as a phasor like what we used to have, where we are going to have it like this. It is going to be in the horizontal. That is where we are going to have your total current in this case. All right, so the total current, that is 3.24. So you can just represent this as 3.24. All right, so this is actually enough for you to obtain all the full marks by just having this. All right, because we are given currents, so you can work with these currents that we are given. Okay, that is to draw the phasor diagram for that circuit. 3 marks for that. This is enough. All right. On question 4, we are given to draw a neat labeled sketch of a half-wave voltage doubler. Okay, so this is, take note, a voltage doubler in this case. Okay, we are talking about a voltage doubler. So this is what I'm having on 4.1 on a voltage doubler. I want you to have this part here. So take note, on the input, that you are given VM, and here we're going to have a doubled voltage, which is 2 times VM, all right? And also the direction of your diodes, which is very, very important. Just 2 marks for that. All right, let's check the other part of the question. Now we are given in this case to explain the operating principle of a half-wave voltage, the same voltage doubler that we had. Now we want to describe its operation. All right, so this is what I'm having. Remember from our previous section, this part that we had, it's actually during, we are going to have 2 cycles in this case on the input, whether that is a half-wave, the first positive and another negative. Okay, so during the positive half cycle, diode D1 is forward biased and conducts charging C1 to VM. So diode D1 is going to be forward biased in this case during the first half cycle, which is a positive half cycle. So we are going to have our D1 charging C1 so that it is going to give us a maximum. Then when it is in the negative, this time the negative part is going to affect D2 so that it will be forward bias in this case. So this is the idea or the concept of this voltage doubler. So during the negative half cycle, diode D2 is forward bias now charging C2 to 2 times VM. That is now having a maximum of voltage being doubled. All right, so that is what we have on the description. On 4.3, we are given now to draw a neat labeled characteristic curve of a photodiode. Remember, a photodiode is the one that takes in light, which is photo. That is, in this case, we have got the resistance in microamps, then the voltage, which is given in volts, then the lags that is increasing. So you can just have the increase in lags from 0 and so on and so on. All right, so this is what we have, just 2 marks for that, which is for characteristic curve. All right, on 4.4, we are now given to explain the operating principle of a photodiode. All right, last time we had the characteristic curve. Now it is to explain the operation. So on the operation, we know that a photodiode operates under reverse biased conditions. When the light falls on the PN junction, the availability of minority carriers increases. The leakage current will increase. As the leakage current increases, the conductivity of the photodiode increases. So this is the description that you are supposed to be having as your best description or attempt this typical question. All right. So that was our question 4, 4.4. On 4.5, we are given the input of a wave. So this is the input of a wave forming to a clipping circuit. All right, so you clip, these are clippers. Draw the wave output of each of the following clippers. All right, a negative series clipper and a positive parallel clipper. All right, so we need the character, the waveform of the output. All right, so the output. All right, so the first part, we are given a negative series clipper. All right, so for a negative series clipper, this is what we have on the output. So this is your V in, then V out is equal to V in minus 0.6 volts. All right, so this is what we are going to have in this case. Then the other part was a parallel, that was a parallel positive clipper. If you are to check for a parallel positive clipper, this is what we are going to have on the output of V out. So this time V out is equal to minus V in minus 0.7 for 0.6 volts in this case. So this is what we have when we are dealing with a parallel one for this part of 5.52 on a positive parallel clipper. Then on 4.6, draw the characteristic curve of a PN diode. The characteristic curve, 2 marks for that. Okay, so for a PN diode, these are the characteristics that we have on our curve. Taking note of your forward voltage, reverse voltage. So you've got the reverse bias region, the forward voltage drop that you're going to have at this point, depending with the diode that we have, is it a silicon, is it a germanium? So that is where we have got those 0.3 and 0.7, or which can be written, let's just say 0.6, approximately 0.7. Okay, the forward bias region. And so this is what we have. Just 2 marks for that. Yeah, it's actually deserves the 2 marks. We do not have a lot there. We just have to sketch our graph properly, our characteristic curve properly. On question 5, draw a neat labeled circuit diagram of a common collector amplifier with take note, it's a common collector amplifier given VCC at 12 volts and its collector resistance value at 2 kilo ohms. So take note, it's a common collector. Take note about this, guys. All right. So this is what I'm having for you guys on a common collector with the given conditions, VCC equal to 12 volts and the RC at 2 kilo ohms. So take note, on the input, your IB, the base current, then the dividers, which is RB1, and these are the voltage dividers, RB1 and RB2. Then the current IC, the voltage out, and the input. This is the most important part for you to obtain the whole 4 marks that you are given in this part. Then from the other part of the question now, we are given to explain or to give 2 characteristics of a common collector amplifier, which is the same amplifier that we had before. What are the characteristics of this amplifier? Okay, so this is what we have on the characteristics of a common collector. That is it has got 180 degrees phase shift between the input and the output, and average input and output impedances, high current gain and high voltage gain. So any 2 from these ones can be accepted on your description. So you can just have 2 from there. All right, on 5.2, we are now given to draw a neat labeled circuit diagram of an RC coupling. Okay, so that's RC coupling, a circuit diagram. So this is what you are supposed to have on an RC coupling on your circuit diagram, showing all the resistors with the bases, the capacitors, 2 capacitors, and so forth. So this is what we got in this case. All right, let's check the other part of the question where we are given to give 2 advantages of a negative feedback. When there's a negative feedback, what are the advantages of that? So we've got improving the stability, reducing distortion, reducing gain, reducing noise, the increasing of the bandwidth, the increasing of input impedance, and the decreasing of output impedance in this case, which is very, very important if you are dealing with this part. So you have to be very, very careful on this part here. All right. Okay, I left this part here. I didn't tick this part. What happened here? Calculate the values from drawing the load line, that is 2.2. Calculate the values for drawing the load line in this case. All right, that is okay. If you checked here on this part, if you are to check what we had from our diagram, where's that diagram here? This is the one that they are talking about. All right, on this other part here, we can have our load line from VCC, which is 12, and R, which is 2 kilos. So we can calculate the saturation current from there, which is the saturation current for IC. So it's going to be IC set in this case, which is equal to VCC. So this is going to be VCC over RC. So you've got VCC, which was at 12. All right, so this is going to be 12 over RC, which is 2 kilo ohms. So 2 kilo ohms, that's 2000 ohms in this case. All right, so this is going to give us the saturation current of 6 milliamps. That's 6 times 10 to the exponent of -3, which is 6 milliamps in this case. All right, so the answer is going to be the 6 milliamps. All right, so that is part of that question. That was the part of the question. In this case, let's check what we are given on the other part of the question, which is question 6. All right, so let's check what we have on question 6 here. So now we are given to explain. Take note, the first part on 6.1 is to explain with the aid of a block diagram, that is with aid of a block diagram, the operation of a frequency counter. That is 8 marks for that, all right, or for that. So if you have to check on a frequency counter, this is what you're going to have on your circuit, the analog input signal to the amplifier. Then we are going to have the time-based input on the end here, the counter, and to the display. So the amplifier amplifies the analog input signal. This is the first part that you have. Then you are given that the Schmidt trigger converts the analog input to a digital signal. From there, the time-based generator produces a pulse which opens the AND gate for a certain time. Then the counter counts the number of pulses, and after that, the counter appears on the display, which is on this part. All right, so these are the steps that you have, and also the best description that you can actually give for this one. All right, on 6.2, we are now given to explain. All right, so this part we are given to explain the operation of a strain gauge. That is 1 mark for that. All right, so what do we have, guys, on a strain gauge? Just 1 mark for that. Okay, so what happens is on the issue of what? Resistance. The resistance of the wire changes with the expansion and contraction because of external applied force. That is what we have on our description in this case. Then on the other part of the question on 6.2, we are given to give 2 applications of a strain gauge, the same strain gauge that we had on the description. What are the applications? So we are going to just take any 2 from these ones. It can be applied on force or pressure, that is aircraft wings or concrete pylons. Then on torque, that is when dealing with a torque bars, that's where we can have strain gauges. On displacement, that is buildings, bridges. If you go to those way bridges that we have, they use the strain gauge operation. All right. Then we are having question 6.4, where we are asked to draw a neat labeled sketch showing the construction of a piezoelectrical transducer. 3 marks for that. All right, so a piezoelectrical transducer is like this, guys. This is what we have. Take note, you're supposed to show these points, mostly the crystal, the plunger, the diaphragm, and the metal plates, together with the metal or plastic bag and these terminals. So make sure that on the diagram, these are properly shown or presented, and you must draw a neat diagram, very, very neat diagram. Then explain the operation of 6.5 of the piezoelectrical transducer, the one that we drew on 6.5. Now they are asking us to explain the operation. All right, so on the operation, when an external force is applied to the crystal, an EMF is generated or is what produced when we apply to the crystal, this crystal here, then an EMF is going to be generated from that external force. So that is what we have on our description. If we move on to question 7, we are given 7.1, where we are given to draw a neat labeled circuit diagram of a non-inverting amplifier. Take note, a non-inverting amplifier. That's 3 marks for that one. All right, so for a non-inverting amplifier, this is what you must have for the non-inverting amplifier. Properly show the points on the diagram, the resistance and everything properly shown. This one, I do not have much to explain. You just need to know your diagrams. All of your amplifiers, you need to know them, okay? Then describe the output waveform of a differentiator with reference to the input waveform. So we are asked to describe the output waveform of a differentiator with reference to the input of what the waveform in this case. All right. So on this part, we must know that the output is actually from, so this op is for the output, So the output wave is going to be 90 degrees out. For a differentiator is going to be 90 degrees out of phase. So this is actually 90 degrees out of phase with the input that is the input waveform in this case, or the input wave. So it's 90 degrees out of what? Out of phase. On 7.3, draw the input and output wave forms of an integrator if a square wave is supplied. Okay, if you use a square wave on the what? On the input, what is going to be the input waveform for an integrator? So you see the part that I was saying, that you're supposed to know each and every part of your amplifiers in this case. All right, so this is what you're going to have. 7.3. Okay, so remember the input is a square wave. All right, we are having the input as a square wave, so this is what we are going to have on our output. All right, so that was our 7.3. 7.4, we are asked to draw a neat labeled waveform to illustrate a cyclotronic control, cyclotronic control. All right, let me check what I'm having here, guys. All right, so this is what I am having on the output, and on the input, we have got the phase control, then the cycle control off, then the phase control, then the cycle control off, phase control, and so on and so on. So this is what you're going to have throughout. All right, so this is the waveform that we are having. All right, then 7.5 is to draw again a labeled circuit that shows how to achieve a full wave control by using the back-to-back connection method. All right, by using a back-to-back connection method, the label diagram. So this is our diagram that we have for a back-to-back connection. We've got our load, then we've got from the triggers that these ones, the transistors that we have, we are going to have the control circuit 1, the control circuit 2, control circuit 1, control circuit 2, then our SCR1, our SCR2 in this case. What is left? Okay, everything. Then this is your input. So you're also supposed to indicate this one as your VIN, which is your input in this case. All right. So in this part, that is how we can actually have a full wave control. Okay, then the last part of our question was to differentiate between line commutation and forced commutation. So definitions, guys, you're supposed to revise your definitions, guys, as much as you can. All right, so on line commutation, we are given it occurs when an AC signal crosses 0 from positive to negative, and the anode becomes more negative with respect to the cathode. For a forced commutation, it occurs when a current is forced to flow in the direction opposite to forward current. It's actually a forced thing that we don't want, that we know it does not, it cannot happen, but we are forcing current to flow in the direction where it is not supposed to be, in a consideration of what? Opposite direction. Just imagine. So that is a forced commutation in this case. All right, so that is what we had from the whole of this paper, which was from February 2022, having a total of 100 marks in this case. So like I said, guys, we we need to revise with more question papers, more revisions as we prepare ourselves for the exams which are ahead of time. Also revise the theory part as much as you can. Yes, here we are just coming to give you what is required in terms of the diagrams, in terms of the explanation. Sometimes you might have your own explanation, but there is a specific explanation which, if you use on your final answers, it is going to be an advantage for you. So that's why we are bringing you these previous exam papers with the theory and diagrams that they used before, so that you can also relate how do they ask and how are you supposed to attempt such typical questions. For now, that's it, guys, from MEMO African Motives on industrial electronics N3. Till we meet again.